Projective grid mapping, or PGM, is a GPU-based technique for generating a terrain mesh entirely from height map data. This means that only 2D textures representing topography are transferred to the GPU. PGM combines raycasting and rasterization to create a terrain mesh on the GPU. PGM was originally applied to ocean wave visualization and was later adapted for terrain offset from a plane. In this work, we address the challenge of applying PGM to a sphere. By adapting PGM to the sphere, we create a planetary algorithm that can visualize a scale model of Mars. Here we see the massive Olympus Mons disappearing behind the horizon to the right. Particular challenges of spherical PGM include capturing the area of the planet below the camera and the area of the planet beyond the horizon, including such large mountains. Source data for this visualization includes global topography from the Mars Orbiter Laser Altimeter and a tinted global color map from the Mars Orbiter camera. In addition, we incorporate high-resolution data from the HiRISE camera aboard the Mars Reconnaissance Orbiter. We will now fly closer to Mars and through Vallis Marineris, the largest known canyon in the solar system. As we travel, notice how the bases of large terrain features pass below the viewing camera but remain visible. Our algorithm adjusts the sampling camera so that it captures these features that the viewing camera does not. In addition, this long, continuous flight path demonstrates the continuous level of detail provided by PGM. As the camera moves, the sampling dynamically adapts since we are raycasting the projective grid each frame. Due to the frame-to-frame spatial coherency between projected grid points on the sphere, the final offset position for any particular grid point gradually morphs as its geographically projected position moves. This completes our traversal of the 4,000-kilometer-long Vallis Marineris. Next, to demonstrate how our algorithm captures the area beyond the horizon, we will travel along the Martian surface towards Olympus Mons. Olympus Mons is the largest known volcano in the solar system. Without the ability to raycast a trans-horizon sphere, PGM would not be able to capture this very large terrain feature when it is behind the horizon. This is important because although the base geographic area from which the mountain would be offset is not visible, it should be visible due to its approximate 21-kilometer height, making it rise up from behind the planet's horizon when covered by the projective grid. We now travel to the Hellas Impact Basin, located in the southern hemisphere of Mars. This area demonstrates the visualization of high-frequency terrain. Next, we zoom in on high-resolution imagery and topography from the HiRISE mission. This is Victoria Crater, which was visited by Opportunity earlier on in its mission. This area demonstrates our ability to display meter-scale data. As we change the camera angle to be parallel to the local surface, the digital terrain model will become apparent. This high-resolution topography was produced by the HiRISE mission using stereo image pairs. Next, we demonstrate the difference between using low and high-resolution data maps for the North Polar region. By implementing the polar stereographic projection, in addition to the simple cylindrical projection commonly used in virtual globes, we avoid graphical artifacts that occur near the poles. Here is a surface feature mapped near the North Pole that demonstrates further the high-resolution data using a polar stereographic projection. Here we show the operation of the PGM algorithm from a third-person perspective. As you can see, the projective grid is raycasted onto the base sphere, capturing only the part of the sphere that is visible. The algorithm maintains the sampling camera so that its frustum is always aligned to the horizon. This is important for maintaining a proper sampling of the planet when the viewer is near the surface. We now zoom in closer to the planet to demonstrate the action of the sampling camera's alignment to the horizon. Here is a close-up sampling of the planet from a third-person perspective. As compared to the far-away view, this sampling captures only a small geographic area. Note that the projective grid shown here is low resolution in order to demonstrate the gradual change in sampling frequency the further away a projected grid point is from the viewer's position. Next, we will pause the algorithm when the viewer is above Olympus Mons to show how the sampling camera captures the area below the viewer. Disabling height offset shows how closely the final terrain mesh can match the sampling and viewing cameras. Finally, we implement deferred texturing to combine height and color maps at runtime on the GPU. These data maps may be toggled on or off.